Welcome to my YouTube channel, Techie Sang. Hi, this is Dr. Sangeeta. If you find and feel that my channel is informative to you, kindly subscribe my channel. We are going to discuss about real-time clocks in embedded system.
The need for timekeeping in embedded system. Many embedded applications require accurate tracking of date and time. Simple example is that data logging, scheduling, time stamps, alarms, power management. The limitation is that it uses system clock for long time. So it depends on power dependency. That is a problem that occurs in this case. In case of real-time clock, we have dedicated clock for clock to maintain accurate time when the main system power is off. So independent power source, battery or supercapacitor is used. So persistent and accurate information, we will get it. Key features and functionalities. Square wave output. Some RTCs provide a programmable frequency square wave output, can be used as a precise clock source for other peripherals. Battery backup switchover. It automatically switches to battery power source when main power fails. So the backup will be restored. That is possible here. Automatic switchover is possible. So it will be uninterrupted. Timekeeping will be possible here. Temperature compensation. High-end RTCs real-time clock may include temperature sensors and compensation circuitry to maintain the accuracy over wide temperature range. Crystal oscillator frequency can drift with temperature. Time and calendar tracking. You can maintain accurate time down to seconds. So including days of weeks, days and month, leap year, everything we can keep it. We can keep it in the device. Alarms. Programmable alarm register to trigger interrupts at specific times or dates. Useful for scheduling events or waking up the main system from lower power states. So, whenever if the system is in a different state, it can be made wake up using alarm. Interrupt generator. A periodic interrupt can also be generated, or on alarm match you can generate the interrupt, or event driven time based actions without constant pooling, you can generate the interrupt. The applications are data logging, time mapping, sensor readings and events, accurate date and time, crucial for analysis and record keeping. Next is scheduling and automation. It triggers the action at specific times, at specific dates. Example, turning on lights, starting process, collecting data at intervals. If you're going to collect the data at the remote at every 10 seconds or every 1 hour or every 1 day or every 1 month, all this is possible using scheduling and automation. Power management. In that case, what we can just do is that we can wake up the main system from the low power modes at scheduled times. And the energy will be optimized. Since I'm making it in the sleep mode, I can optimize the energy. User interface. Displaying the current date and time on embedded system. So providing time-based user interaction. In case of network device, IoT, the synchronization with network time servers for accurate timestamps, and coordination is required. For real-time operating, this we have seen earlier. Real-time operating system provides a time base for task scheduling and delays. In-circuit emulator for embedded system. The challenge of embedded system debugging is that traditional debugging interfaces display, keyboard, and advanced logging. This is the challenge that occurs in embedded system debugging. And observing internal states of CPU register and memory, it is very difficult. Software and hardware is tightly coupled, and if I want to isolate and issues, if there is a complex issue, then I cannot identify it. It is very difficult to identify. It is a very challenging problem. And early development stages may have limited or non-functional target hardware. Introducing the in-circuit emulator, hardware debugging tools that provides deep visibility and control over target embedded system during development. Historical perspective is that it replaces the target CPU with an emulator. Modern ICE is that it uses built-in debug features, JTAG and BDM. The core idea is that it has ability to run the step through and inspect the target system behavior in real time. That is possible in case of in-circuit emulator. So we have covered basic principles of operation, how modern IC connects to target, key features and modern capabilities, advantages and disadvantages. Original concept is that CPU emulation, historically what it does is that it replaces the target microcontroller or microprocessor with its own more powerful processor, which is capable of debugging functions. That is what it does. And it connects to target board CPU socket. The emulator would mimic the target CPU behavior while providing the debugging control. This is a historical emulation we do, and modern approach is that it integrates microprocessor and microcontroller have integrated debugging interfaces. That is joint test action group, that is JTAG, and background debugging mode, BDM. This is possible here, and IC connects to this debug ports on the target board. It utilizes target CPU itself for execution and also gains control over the debug interface. Basic principle of operation is that the host computer and debug software. What it does is that it bridges between the target system and the host computer running debug software. That is what IC does. So, it is an often part of IDE. Debugger provides a user interface to control the target execution and set breakpoints, inspect memory, and registers. Real-time operation with control. ICE allows the target system to run at its full speed while still behaving under the developer control. So breakpoints can halt execution at specific points without significantly altering the system behavior. The main advantage is that deep visibility, real-time debugging, hardware-assisted breakpoints, powerful control, early-stage debugging, complex problem-solving, non-intrusive modern ICE. This is a major advantage what we have seen it. In case of disadvantage, the problem is that it is more expensive and it is also more complex. The setup and configuration, it requires proper setup and configuration of the debugger software. And target hardware dependency, it requires functional target board with a debug interface. Potential for hardware issues. Incorrect IC connection can potentially damage the target hardware itself. It will damage the total target hardware. Decreasing reliance. With advancement on-chip debugging, software-based tools, the necessity of full-fledged IC might be less for simpler projects. When to use an IC in the development cycle? It has to be used in early hardware-software integration and complex and intermittent bugs, real-time system debugging, where time is sensitive, low-level driver development, where there is direct hardware access and register manipulation, bootloader and firmware development, analyzing the initial stages of system startup, performance analysis. It analyzes the bottlenecks in critical code section. Intertwined nature and hardware and software in embedded system. In case of traditional, it directly depend on hardware. So software issues can be symptoms of deeper hardware problems. So the problem will not be that much, software issue will not be that much problem in case of traditional software development. In case of debugging, it requires both domains and their interaction. The challenges in hardware debugging is that limited visibility into hardware states when compared to software. Difficulty in isolating hardware faults from software bugs. Potential for physical damage during probing or testing. Requirement for specialized tools and knowledge. Intermittent hardware failures can be particularly challenging. The importance of effective hardware debugging. It ensures correct functionality and performance of the embedded system, identifying and resolving manufacturing defects, and also validating hardware design and specifications. It reduces time and cost. The overview, what we have covered is that common hardware issues, essential hardware debugging tools, key debugging techniques and methodologies, strategies for isolating hardware and faults, best practices for hardware debugging. The common types of hardware issues is that power supply problem, that is insufficient voltage or current, voltage drops or fluctuation, incurrent polarity, power rail, shorts or opens. Clocking issues, incorrect oscillator frequency, missing clock signals, unstable or noisy clock signals. Interconnect problems is that open circuits, that is if it is broken. If it is shorts, there are two rails that runs. If it is shorted by somehow, in that case, this problem will occur because of incurrent wiring or connections. Component failures, defective integrated circuits, faulty passive components, and damaged sensors and actuators. Signal integrity issues, noise and interference on signal lines, reflections and impedance mismatches. You have to calculate the impedance properly. If there is mismatch in impedance, so this issue will occur. The crosstalk between signals, and you have memory problems, faulty RAM or flash chips, incorrect memory addressing or configuration. And next thing is data corruption. Interface problem, incorrect protocol implementation at the hardware level, I2C, SPA, UART, example, all these things can be used, and timing mismatches between communication devices. Incorrect signal levels. The essential hardware debugging tools are digital multimeter, oscilloscope, logic analyzer, power supply, function generator, soldering iron and rework station, visual inspection, power rail verification, clock signal analysis, continuity and short circuit testing. Okay. Digital multimeter, okay. Oscilloscope, okay. Logic analyzer, you people would have done it. Power supply, you have to adjust the power to the target board. We have just seen what are the problems that occur if power supply, if proper voltage, incorrect voltage or current is fed, and testing power consumption, simulating different power conditions, and function generator. It generates square, sine wave, square wave, triangle waves at different frequencies. And then soldering iron. If you want to join the repair everything with soldering irons, you should be very careful. And visual inspection. You can inspect visually the PCB board. And then power rail verification. The rails that occurs in the board that can be inspected. Whether shorts has occurred or not, that we can inspect it. Clock signal analysis. Oscilloscope to verify the presence, frequency, and stability of clock signals at the oscillator and critical components. Continuity and short circuit testing. Digital meter is used to check it. The key hardware debugging techniques is that signal tracing, component isolation, substitution, JTAG, divide and conquer approach. That is, you will divide it into smaller blocks, and each block is tested individually. That is what it happens. The best practices is that work methodologically and also systematically. And you should be very patient and persistent. You have to use right tools. You have to double check connections and settings. You have to exercise caution to avoid damage. Collaborate with software designers. Learn from mistakes. That is what hardware failures that occurs earlier, and you have to improve your debugging skills and your design practice. This is what you have to do it. Thank you all.